Okay, so welcome to the last lecture of this course. So today we will complete the proof of inverse function theorem. Now let us just recall what we have already seen for a function of one variable. So we had f from interval a b to r, and we assume that f prime is continuous and at some point x naught in a b we had f prime x naught not equal to 0. So from that what we did actually, that we can actually find a smaller interval a naught b naught. We proved all these things in the last lecture. A b, where f is actually 1 1 and f of a naught b naught is open. So whatever we proved actually boils down to this thing. So if you look at carefully what we did, that we choose some interval where f prime is non-zero. This interval was chosen in such a way that f prime is non-zero in the entire interval, and f prime a and f of a naught and f of b naught are both are different from f at x naught. Then we actually saw that one can find given any y in f of x naught minus m by 2, if you look at the previous lecture, plus m by 2, where m was f of a naught minus f of x naught, which we assumed without loss of generality one of them will be, and call that m, and if we took that, then for each y there exists z in a naught b naught such that f of z equal to y naught, z naught maybe in the open interval. It is not one of the endpoints. It needs little work to, it just, if you look at the proof, you actually see that this z naught will be unique. Now this was the case for f from an interval to taking values in R. Now suppose I have this situation. And f is from u to R. So instead of f prime continuous, I will assume f has all partial derivatives del fi del xj continuous on u. Recall that we can always write f as f1 f2 fn, and I have a point x naught in u where I assume that instead of f prime x naught non-zero, exact analog of that is the Jacobian has non-zero determinant, that is Jacobian matrix is invertible. Then, so this is the same setup, and here it was conclusion 1, 2. Then there exists a smaller interval in U where f is 1 1, and in that interval the image of that interval is open. So, whatever is there, I wrote the same thing here in for the case of function from Rn to Rn. And proof, here I write exactly same as in the case of f from A B to R, that is whatever we had yesterday or whatever the summary is written here in this case, except plus we needed to find this interval A naught B naught. So, here and that interval you can find because of continuity of these partial derivatives, and where we define this function, you recall h x equal to, here after choosing y we define the function h x equal to f x minus y. Here you have to observe, you will define the same thing, but in this case h x has to be replaced by mod f x minus y in this interval, and you have to observe this one and another observation, that this determinant j f x is continuous. If I give this condition that this del xj continuous, the determinant is also a continuous function, and the proof follows exactly same pattern. So, let us now, with this observation, let us now prove inverse function theorem. Okay. So, let me state inverse function theorem first and then prove it. So, this proof, this analog, I leave it as an exercise. Okay, here goes the statement of inverse function theorem. So, let me follow the standard statement from some. So, this statement is, so while writing the statement of a theorem, is always better to follow a standard book. In this case, I am following the statement from Apostol Mathematical Analysis with the notational changes maybe. So, let we start with U in Rn and f from U to Rn be continuously differentiable, be such that all partial derivatives are continuous. So, let x naught is a point in U and determinant of g f x naught is not equal to 0. Then there exist an open ball, or you can set open set. I can make, let us say, theta 1 inside U and open set theta 2 in Fu. X naught is in theta 1, f of x naught is in theta 2, and a unique g from theta 2 to theta 1 such that g is the inverse, that is f g y equal to y for all y in theta 2 and g f x is equal to x for all x in theta 1, and since I have taken f to be C1, I also get g is differentiable, and this fellow is simply Jf at Gy, this determines Jacob matrix inverse. So, if you, this is true for any n. So, if you read it for interval, it will look like, so suppose f is defined interval to r, n is 1, and f prime is continuous with some x naught, f prime at x naught not equal to 0, then there exists an open interval inside that interval a b, smaller interval, and an open interval in f of a b such that I can write f g y equal to y and this thing, and so I can define an inverse, and g prime of y equal to f at g y inverse, that is 1 upon f at g y. So, you should be able to interpret it as when n equal to 1 case. Okay, I will prove this, and the proof will use, as I said before, implicit function theorem. And because of that, as the name suggests, implicit function theorem, actually if I give you an f u, to actually get that g, this may not be easy, because one may not actually, whatever uses implicit function theorem, to get hold of this, the particular function may not be easy or may not be possible even for some f. I mean, given an expression for f, you may not be able to write down the expression for g. So, it is the existence theorem only, and that is true for anything as implicit function theorem, but with the no knowledge of existence, we can do lot of things when you go ahead, particularly when you do geometry. This existence of inverse function and implicit function, that is a great help. So, maybe if you do a course on geometry later on, differential geometry, you will see how it is used left and right. Anyways, remember the statement here, I just erased. So, this condition is same, conditions are same here, and remember these two observations that I will have these two. Okay. So, I will use these two observations written on this board. So, let us start the proof. Okay, let us get rid of this u fellow, and u theta, I mean f may not be 1 1 on entire u, but here f will be 1 1 in this thing. So, what I from the previous observation, maybe by shrinking u, we may assume, or we assume f is 1 1 on u, otherwise go to some ball around x naught, because after all it is a local statement. So, go to some ball inside u around x naught where f is 1 1. Now, consider this function, let us say capital phi from u cross Rn to Rn phi xy equal to fx minus y. Okay. So, what is del phi I, phi j, del xj? So, phi I can write phi 1, phi 2, phi n, each phi I from u cross Rn to R. So, when I have x variable, this is this side fx minus y. So, this is precisely del fi minus. So, look at that, this phi I will be fi minus yi. So, this will be del fi del xj. And if I have del phi I, if you look at del phi I del yj, this will be simply minus 1 minus delta ij, right? Delta ij matlab that is minus 1 if I equal to 1, I equal to j, 0 otherwise. So, phi has continuous partial derivatives. Correct. Now, you see I have actually come to the setup of implicit function theorem. Phi is from u cross Rn to Rn, del phi I del xj, del fi is del fxj. Therefore, given this assumption, what I have, the determinant of j at fx naught is non-zero, I get this matrix I equal to 1 to n, j equal to 1 to n, determinant of this fellow is not 0. So, I have two components of phi u and Rn. On the u component, this del phi del xj is same as the determinant of del fi del xj, because this is actually non-zero. This matrix is precisely the Jacobian matrix. Okay. At the point, so this is at the point x naught f x naught Okay. Now, I can use implicit function theorem, which will say that there exists theta 2 in R n and g from theta 2 to u, or you take g of theta 1, g of theta 2, which is theta 1, such that what happens? That the first component is u, second component is this thing. So, phi of g y y is equal to f g y minus y, which is actually 0. Okay. So, that gives f g y y equal to, sorry, this will give if g y equal to y. How did I use implicit function theorem? See, I had phi of x naught f x naught, this is 0, right. So, I am applying to this thing, phi of x naught f x naught 0. So, there exists a theta 2 where f g y y will be equal to 0, but f g y y is this fellow, f by definition f g y y. Maybe I should have written it. This is equal to 0 equal to by definition f g y minus y. So, that gives you f g y equal to y, and that is the inverse of f. And here actually if you do not like this, so let it be in u, and since f is 1 1, this f inverse of theta 1 theta 2, call it theta 1. This is actually will be g of theta 2. So, that is your existence of theta 1. So, this is an open set. If theta 2 is open, f is continuous, f theta 2 is open. So, and being open and 1 1, since f is 1 1, this also gives, or x in theta 1 implies g of f x equal to x. This is by 1 1ness again. Okay. So, that gives the existence of g, which is actually the inverse of f. And what about the derivative? It is very easy. You see, g f x is x. So, if I apply chain rule, then what do we get? That, so apply chain rule to take derivative, that will give you j g at f x compose with j f x is the Jacobian determinant of the function x going to x, which is identity. So, function x going to x, if I call this function h, then j h of x is simply identity, right. So, that shows that j g at f x, which is y, equal to j f x inverse. And that is the proof of inverse function theorem, which directly use implicit function theorem here. So, G is this again you see this G, the derivative we get sorry inverse we get, it comes through implicit function theorem. So, that is what I said, that it may be difficult to calculate given an f, because implicit function theorem gives existence only, it does not give construction. So, inverse function theorem also gives existence only, does not give construction of G, but still it is very useful. So, that will be the end of the course. From here you can go to two things. One is you can go to the multivariate integral calculus, since you now know Jacobian, determinant, everything, you can go to multivariate integral calculus, or you can go to differential geometry, where you need less integral calculus, you may need very less, you actually need the whatever background we have done here in this course. So, some elementary course in differential geometry you can take up from here. Okay, that is it. Thank you everybody.